Hello everyone, this is Nirali Patel from New Alger Institute of Engineering and Technology. In today's lecture, we are going to discuss about bounds on probabilities topic, and after that, we will discuss about Chebyshev's inequality to find out the bounds on probability. So let's first discuss about what is the bounds on probability. So as we know that the probability distribution is given for any random variable x, then we can easily calculate E of x, that is nothing but the expected value of x and the variance of x. But if the E of x and the variance of x is given, then probability distribution of x cannot be constructed, and quantities such as P of mod x minus E of x less than or equal to k cannot be evaluated. So there are several approximation techniques that is used to find out the upper and the lower bound for such probabilities. So in order to find out the upper and lower bound of probabilities, the one more important technique is Chebyshev's inequality. So let's start with the Chebyshev's inequality. So the Chebyshev's inequality is used to find the upper bound and the lower bound of the probability. So if x is a random variable with mean mu and variance sigma square, then for any positive number k, probability of mod x minus mu greater than or equal to k sigma square is less than 1 upon k square. Or we can say the probability of mod x minus mu less than k sigma is greater than or equal to 1 minus 1 upon k square. So let's see the proof for this too. So first, let x be the continuous random variable. So we can write sigma square, that is nothing but the variance of random variable x is given by E of x minus E of x whole square. Now E of x is nothing but mu. So we can write E of x minus mu whole square. And if x is continuous random variable, so we can give the variance of that continuous random variable x through the integration minus infinity to infinity x minus mu square f of x dx. This term of integration can be divided into three parts. The first integration from minus infinity to infinity mu minus k sigma x minus mu square f of x dx plus integration from minus mu minus k sigma to mu plus k sigma x minus mu square f of x dx plus integration from mu plus k sigma to infinity x minus mu square f of x dx. So see, over here this x minus mu square is always greater than 0 or equal to 0, and that is the positive term. And f of x is always greater than or equal to 0 because the f of x is nothing but the PDF of the random variable x. So we can say that this second term is always greater than or equal to 0. So if the second term is always greater than or equal to 0, so summation of this three term is always greater than or equal to the summation of this three term is always greater than or equal to summation of first and the third term. So from that we can write greater than or equal to the integration from minus infinity to infinity mu minus k sigma x minus mu square f of x dx plus third time is also as it is. So integration from mu plus k sigma to infinity x minus mu square f of x dx. Now we know that the x is less than or equal to mu minus k sigma and x is greater than or equal to mu plus k sigma. So we can write x minus mu mod x minus mu greater than or equal to k sigma. Now we substitute this value in the equation number 1. So from that we can write sigma square is greater than or equal to minus infinity to infinity minus infinity to mu minus k sigma k square sigma square f of x dx. So here instead of this x minus mod x minus mu greater than k sigma, so if we take the square both sides, so we can write x minus mu square k square sigma square and over here greater than or equal to, so here I have to put the greater than or equal to. So instead of k minus mu square, what I'm doing, I'm putting this value x minus mu square is replaced with k square and sigma square. So minus infinity to infinity minus infinity to integration from minus infinity to mu minus k square f of x dx plus integration from mu plus k sigma to infinity k square f of x dx. So we have just simply put this value in this equation number 1. Now k square sigma square become common because k is also constant and sigma square is also some kind of constant value. So in bracket we can write now integration from infinity to mu minus k sigma f of x dx plus integration from mu plus k sigma to infinity f of x dx. K square sigma square as it is. Now we know that if we want to find out integration from minus infinity to infinity f of x dx, so that is nothing the probability of x less than or equal to a. So here integration from minus infinity to mu minus k sigma f of x dx is probability of x less than mu minus k sigma. Similarly, for this term, probability of x greater than mu plus k sigma. So we can write k square sigma square. Now this mu comes this side, so x minus mu less than minus k sigma plus p of x minus mu greater than k sigma. Now k square sigma square and this term is written as the probability of mod x minus mu greater than k sigma, because as we have discussed, this x minus mu less than minus k sigma and x minus mu greater than k sigma is nothing but mod x minus mu greater than or equal to k sigma. So from that we can write probability of mod x minus mu greater than k sigma. Now that is equal, so sigma square greater than k square sigma square probability of mod x minus mu greater than or equal to k sigma. So now the sigma square is come over here and the k, so 1 upon k square greater than probability of mod x minus mu greater than or equal to k sigma. So we can write p of x minus mu, p of mod x minus mu greater than k sigma is less than or equal to 1 upon k square. Now we know that these two are the mutually exclusive, because this is suppose our mu, this is our mu minus k sigma and this is our mu plus k sigma. And now if we are saying that mod x minus mu greater than k sigma, then x is lies between this, suppose this is our final edge, or this. And if we are saying that x minus mu less than k sigma, then x lies between this two. So here x lies between this or this. So because of that, we can say these two are the mutually exclusive. So we can write p of mod x minus mu greater than k sigma plus p of x minus mu less than k sigma is equal to 1. So p of x minus mu less than k sigma is equal to 1 minus p of x minus mu greater than k sigma. Now p of x minus mu greater than or equal to k sigma is nothing but less than or equal to 1 upon k square. So we can get the utmost value for this is 1 upon k square. So this is the maximum value for this term. So if we put this maximum value of this term, so we can get this minimum value for this term. So we can write p of mod x minus mu less than k sigma is greater than or equal to 1 minus 1 upon k square. So this way we have proved this two equation. So now let's see some knot. So if k sigma is c and that is greater than 0, so instead of k sigma, if we put the c over here, so p of x minus mu greater than c less than 1 upon k square. But the 1 upon k square, so here K sigma is equals to C. So K square into sigma square is equals to C square. So we can write 1 upon K square is equals to sigma square upon the C square. So from that, probability of mode x minus mu greater than or equal to C is less than or equal to sigma square upon the C square. And similarly, the probability of mode x minus mu less than C is greater than or equal to 1 minus sigma square upon C square. Now, to find out the lower bound of the probability, we can make use of this Chebyshev inequality. That is, probability of x minus mu less than k sigma is greater than or equal to 1 minus 1 upon t square, or probability of x minus mu less than c is greater than or equal to 1 minus sigma square upon c square. Similarly, to find the upper bound, so for that, probability of mode x minus mu greater than k sigma is less than or equal to 1 upon k square, or probability of mode x minus mu greater than or equal to c is less than or equal to sigma square upon c square. So this is all about for today's lecture. In next lecture, we will discuss example on this topic. Till then, keep exploring and thank you.